Welcome, students! Today we are going to tackle a classic yet fundamental challenge in high school mathematics: numerical sequences. This isn't just any problem, it's a final exam level task designed to build your rigor and logic. Our mission today is not just to find the answers, but to master the step-by-step resolution. Think of sequences like U sub n as stories that unfold one step at a time. By the end of this interactive whiteboard lesson, you'll see that even the most complex-looking fractions can be tamed with the right strategy. Let's ignite that light bulb of curiosity and dive in. Before continuing, don't forget to subscribe, like, share the video with your friends, and also leave comments, because that really encourages us to keep creating this kind of content. Before we get lost in the numbers, let's look at our roadmap. We have structured this problem into 3 clear tiers, like climbing a mountain. Tier A is our foundation. We define the sequence, calculate the first terms, and use proof by induction to find its boundaries and direction. Tier B introduces a secret weapon, the auxiliary sequence Vn. This allows us to find an explicit formula and determine the final destination, the limit of our original sequence. Finally, Tier C brings in technology. We will translate our mathematical findings into an algorithm to see how a computer handles these steps. This divide and conquer approach is exactly how top mathematicians solve complex problems. Ready for part A? Every journey starts with a first step. Here is our problem statement. We are looking at a sequence, U sub n, defined for all positive integers n. Notice 2 key pieces of information. First, the starting point, U sub 0 equals 5. This is the seed from which everything grows. Second, the recurrence relation. U sub n plus 1 equals 3 minus 10 over U sub n plus 4. This formula tells us that to find any term, we must look back at the one right before it. Teacher's tip: don't let that fraction scare you. It's just a rule. If you know where you are now, U sub n, you can always find out where you'll be next, U sub n plus 1. Let's start crunching some numbers. Let's put our formula to work by calculating U1 and U2. To find U1, we inject our starting value, U0 equals 5, into the formula where UN is. So U1 equals 3 minus 10 over 5 plus 4. This gives us 3 minus 10 over 9. To subtract these, we need a common denominator. 27 over 9 minus 10 over 9 equals 17 over 9. That's our first exact value. Now, for U2, we inject U1, 17 over 9, back into the same machine. U2 equals 3 minus 10 over 17 over 9 plus 4. Let's simplify that bottom part. 17 over 9 plus 36 over 9 equals 53 over 9. Now, 10 divided by 53 over 9 is the same as 10 times 9 over 53, which is 90 over 53. Finally, 3 minus 90 over 53 becomes 159 over 53 minus 90 over 53, which equals 69 over 53. Great job! We've proved we can handle the arithmetic. Now, let's look at the bigger picture. Now, we're going to use one of the most powerful tools in math, proof by induction. Think of it like a row of dominoes. Step 1, base case. Does the first domino fall? Since U0 equals 5 and 5 is greater than 1, yes! Step 2, inductive step. We assume a domino falls, UN greater than 1, and try to prove the next one must fall too, UN plus 1 greater than 1. We build UN plus 1, starting from UN greater than 1. Add 4 to both sides, UN plus 4 greater than 5. Now apply the inverse. 1 over un plus 4 less than 1/5. Note the sign flip. Multiply by -10. -10 over un plus 4 greater than -2. Sign flips again. Finally, add 3. 3 minus 10 over un plus 4 greater than 3 minus 2, which means un plus 1 greater than 1. Step 3, conclusion. Because the first fell and each triggers the next, un greater than 1 for every single n. It's a chain reaction of truth. To understand if our sequence is going up or down, we need to calculate the difference, u sub n plus 1 minus u sub n. This looks messy, but we have a target. On the left, we start our calculation. Replace u sub n plus 1 with its definition and subtract u sub n. We find a common denominator, which is u sub n plus 4. This gives us 3 times u sub n plus 4 minus 10 minus u sub n times u sub n plus 4 all over u sub n plus 4. Expanding the top, we get 3u sub n plus 12 minus 10 minus u sub n squared minus 4u sub n, all over u sub n plus 4, which simplifies to negative u sub n squared minus u sub n plus 2 all over u sub n plus 4. Now, look at the target on the right. If we expand 1 minus u sub n times u sub n plus 2, we get u sub n plus 2 minus u sub n squared minus 2u sub n, which is exactly negative u sub n squared minus u sub n plus 2. They are identical. We have successfully transformed a messy difference into a clean, factored form. This is algebra at its finest. Before continuing, don't forget to subscribe, like, share the video with your friends, and also leave comments, because that really encourages us to keep creating this kind of content. Now that we have our factored difference, we can finally deduce the variation, the movement of our sequence. We look at the sign of each piece. Piece 1, 1 minus un. Since we proved by induction that un is greater than or equal to 1, then 1 minus un must be negative, or 0. Piece 2, un plus 2. Since un is at least 1, adding 2 makes it definitely positive. Denominator, un plus 4, also definitely positive. So our whole fraction is negative times positive divided by positive, which equals a negative result. This means un plus 1 minus un is less than or equal to 0. Conclusion? The sequence un is strictly decreasing. It's sliding down toward a limit, just like the little graph on the right shows. Science in motion. Welcome to Part B. Sometimes a sequence is too stubborn to reveal its secrets directly. That's when we use the auxiliary sequence trick. We define a new sequence, Vn, equals un minus 1 over un plus 2. Our goal? Prove Vn is geometric. To do this, we calculate Vn plus 1 and hope it's just Vn multiplied by a constant. Step 1. Substitute un plus 1 into the definition of Vn plus 1. It looks like a fraction inside a fraction nightmare, but don't panic. Step 2. Simplify. After clearing the denominators and grouping terms, we get Vn plus 1 equals 2un minus 2 over 5un plus 10. Step 3. Isolate. Factor out a 2 on top and a 5 on the bottom. We get 2/5 times x plus 1 over x plus 2. Look at that! That bracketed part is exactly Vn. So Vn plus 1 equals 2/5 Vn. It's a geometric sequence with a ratio q equals 2/5. Success! Now that we know Vn is geometric, we can write its explicit formula. Vn equals V0 times q to the n. By plugging in U0, we find V0 equals 4 over 7. So Vn equals 4 over 7 times 2 over 5 to the n. We also need to prove that Vn is never equal to 1. Why? Because later we will divide by 1 minus Vn, and you can't divide by 0. Look at the logic. 1, the ratio 2 over 5 is between -1 and 1. 2, this means the sequence is decreasing toward 0, since V0 is positive. 3, therefore Vn will always be less than or equal to its starting value, 4 over 7. Since 4 over 7 is less than 1, Vn can never reach 1. It has a ceiling below the danger zone. Perfect. We have the formula for Vn, but we really want to go back to our original sequence, Un. This is like unraveling a knot using algebra. We start with Vn equals Un minus 1 over Un plus 2. Step 1, cross multiply to get Vn times Un plus 2 equals Un minus 1. Step 2, expand to get Vn Un plus 2Vn equals Un minus 1. Step 3, group all terms with Un on one side. Vn Un minus Un equals -1 minus 2Vn. Step 4, factor out Un. Un times Vn minus 1 equals -1 minus 2Vn. Step 5, divide by Vn minus 1. We can do this because we just proved Vn does not equal 1. To make it look prettier, multiply the top and bottom by -1. We get the final extracted formula. Un equals 2Vn plus 1 over 1 minus Vn. We have bridged the gap between our two sequences. Before continuing, don't forget to subscribe, like, share the video with your friends, and also leave comments, because that really encourages us to keep creating this kind of content. It's time for the grand finale of Part B, finding the limit. Where does Un go when n goes to infinity? First, look at Vn. Since its ratio is 2/5, a fraction smaller than 1, the term 2/5 to the n vanishes to 0 as n grows. So the limit of Vn is 0. Now we use our bridge formula for Un and replace Vn with 0. The limit of Un becomes 2 times 0 plus 1 divided by 1 minus 0 equals 1 over 1 equals 1. Look at the graph. The sequence starts at U0 equals 5 and slides down, getting closer and closer to the line y equals 1, but never crossing it. We have mathematically predicted the infinite future of this sequence. Now let's enter Part C and talk to a computer. We want to find the first rank n where Un becomes strictly less than 1.01. This is a threshold algorithm. When coding, we use a while loop. Here's the trick. A while loop runs as long as the condition is true. If we want to stop when Un is less than 1.01, we must tell the computer to keep looping as long as Un is greater than 1.01. Look at the pseudocode on the screen. We start with U equals 5, n equals 0. The loop says while U is greater than 1.01. Inside, we increment n and update U using our recurrence formula. As soon as U drops below 1.01, the condition becomes false, the loop breaks, and the machine gives us our answer. Human logic meets machine efficiency. Let's see the machine in action. By running the algorithm, we can track the terms one by one. At n equals 0, U equals 5. At n equals 1, U is about 1.889. At n equals 2, U is about 1.302. We keep going. At n equals 5, the value is roughly 1.108. Since 1.108 is still greater than or equal to 1.01, the loop runs one more time. At n equals 6, the value becomes 1.008. Finally, 1.008 is less than 1.01, so the condition u greater than or equal to 1.01 is no longer true, and the loop stops. The value returned is 6. This means that from the 6th rank onwards, all terms of our sequence are strictly less than 1.01. Let's step back for a moment. Look at how beautifully everything is connected. Part A told us the behavior. The sequence starts high and always decreases. Part B gave us the destination. Math tells us it is heading toward 1. Part C provided the verification. The computer confirms it crosses the 1.01 threshold exactly at n equals 6. Theory equals practice. This is the heart of mathematics. Multiple perspectives, algebraic, analytical, and algorithmic, all converging on a single coherent truth. You aren't just doing calculations, you are observing a logical universe. Before continuing, don't forget to subscribe, like, share the video with your friends, and also leave comments, because that really encourages us to keep creating this kind of content. To wrap up, let's fill your teacher's toolbox with the gold nuggets from today's lesson. 1. Induction is your best friend for proving inequalities. Remember the 3-step domino rule. 2. To study variation, always calculate the difference, un plus 1 minus un. 3. Geometric sequences are powerful because they have explicit formulas. 4. Be careful with inequality signs. They flip when you multiply by negatives or take inverses. 5. Loops and algorithms use the opposite of your goal. Congratulations! You have fully mastered this complex final exam problem. Keep that confidence high, and I'll see you in the next lesson.